Welcome to my Science and Maths YouTube channel. Today's discussion Hilbert action and Deriving FA.
Hello dear friends, welcome to my channel. Today's discussion is Hilbert action, Lovelock's theorem. Okay, I have already written what is Hilbert actions and Lovelock's theorem. Now let me discuss that it is called also Einstein-Hilbert action. This is called Einstein-Hilbert actions. Why friends? Because Einstein-Hilbert action in general relativity is the action. Hilbert action is the action that yields Einstein field equations. Okay, we get EFE, Einstein field equations through the stationary action principle with the plus minus plus plus matrix signature, minus plus plus matrix signature. It is the matrix signature. Okay, so Lovelock's theorem is G mu nu and nu is equal to 0. Okay, so in here you see that it is det G mu nu. Okay, det G mu nu means it is the metric tensor. This is metric tensor. Okay friends, I have already discussed what is metric tensor. It is metric tensors. So an R stands for Ricci scalar. Okay, R stands for Ricci scalar, and now it can be written in this way. SH also S is equal to, it can be written this way, S is equal to 1 by 2k R root over minus G into d4x, where k is equal to Einstein gravitational constant. Einstein gravitational constant. Okay, this is called Einstein gravitational constant. Friends, I have already published Einstein field equations and I also discuss what is Einstein field equation. Now I discuss Einstein gravitational constant k, and this k value you can say that k is equal to Einstein gravitational constant is equal to 8 pi g into c to the power minus 4. Okay, so this is the Einstein gravitational and G for gravitational constant. Okay, G for gravitational constant, Einstein gravitational constant, and G for gravitational constant. So it does not converge. S is no longer well defined and modified definitions. Okay, still yields the Einstein equations as the Euler-Lagrange equation of the Einstein-Hilbert actions. Euler-Lagrange equation, Einstein-Hilbert actions. So deriving equation of motions from deriving equation of motion from an action has several advantages. First, it allows for easy unifications of general relativity and other classical fields theories, which are as formulated in terms of an action. In the process, the derivations identifies natural candidate for the source term coupling the metric to matter fields. Okay, and moreover, symmetries of the actions allow for easy identifications of conserved quantities through Noether's theorem. And now I discuss what is the Lovelock's theorem. Lovelock's theorem states that for any arbitrary pseudo-Riemannian manifold M 0,2 symmetric tensor is divergence free and G mu nu is equal to nu, and Lovelock's theorem 2 states that for Lagrangian density Euler-Lagrange equations can be written and this way. These two theorems are very, very important for deriving Einstein field equation. Hello dear friends, we discuss derivations of Einstein field equation. SH is in order to build action, SH will be take a scalar R such that its variations remains the invariant. From the physical point of view, we know that for the metric field G is Ricci scalar and R is Ricci scalar. Okay, R is Ricci scalar, G is matrix field. Hence we can write this equation. This is my Hilbert action, and now I vary a small changes, that is the del SH. This is the small change. Okay, small change del SH is equal to del dx to the power 4 d minus root over d. Okay, and now I introduced, okay, Leibniz rule. Okay, I use Leibniz rule. You know also Leibniz rule. So Leibniz rule I use in here, and we get these equations. Okay, we get these equations G mu nu del G mu nu. Okay, and using the variations is in Ricci curvature. This is Ricci curvature, variation of Ricci curvature. This is variation of Ricci curvature. Ricci curvature. So I get this equation. Okay, using, okay, and now you see that I keep right. This equation is omega 1 and this equation is omega 2. This equation is omega 1 and this equation is omega 2. Okay, this equation, now I just try to show this equation equals to 0. So I use few theory. This theorem is the manifold smooth omega is smooth manifold. Okay, omega is smooth manifold. For this theorem is very for a smooth manifold on omega with boundary. This is the boundary. Boundary we can define. This is, and omega is a smooth compact form. Okay, and another factor is, this is the Stokes theory. You know what is the Stokes theory? Stokes theorem is usual divergence theory. Okay, n is a normal. This is a normal vector. N is normal vector. Now friends, we discuss that using Stokes theorem to convert the integral 4d to 3d, we convert it 4d to 3d. It is 4d to 3d, and we get the value is 0. Now you see del S is this portion, and now Einstein field equation for vacuum, we get this equation equals to 0, and G mu nu we can say Einstein tensor. This is called Einstein tensor. Okay, Einstein tensor is equal to G mu nu is equal to 0. And Bianchi identity, friends, I have already discussed in my channel what is Bianchi identity. That then you can understand G alpha nu is equal to del nu and G mu nu, and with cosmological constant R mu nu is equal to minus half R G mu nu, and lambda G mu nu is equal to K T mu nu. Okay, with cosmological constant. And okay, cosmological constant is, this is the cosmological constant. Okay, this is called cosmological constant. Now we can write this way. This is the del mu nu and G mu nu and K T mu nu. Now what is I use? I use Lovelock theorem. This is my Lovelock theorem. This is my Lovelock theorem. Lovelock theorem 1, because I have already discussed what is Lovelock theorem. Lovelock theorem 1, and next I use, friends, we discuss derivation. So friends, this is Lovelock theorem 1. Okay, now next I will discuss where I use Lovelock theorem 2. Okay, so in here I used Lovelock theorem 2. Okay, Lovelock, according to the Lovelock theorem, I get, also I discuss SH is equal to SM plus KSM. Okay, so now I used Lovelock theorem 2 and I get this value equals to 0, and now simple derivatives, and I proved Einstein-Field theorem. This is my Einstein-Field theorem. This is my EFE. Thanks for watching. I hope my video is very helpful for all people. Okay, this is my discussion is with matter field. When I used matter field, then I can say S is equal to SH plus KSM. Okay, in here SM is the matter field, action is matter field. So I use, and after that I use the variation with, we can write variation in action del S using field Lagrangian. Okay, I used field Lagrangian. This is my, I use field Lagrangian. Thanks for watching. I hope this proof is very interesting for every physics learner. So friends, this is Lovelock theorem 1. Okay, now next I will discuss where I use Lovelock theorem 2. Okay, so in here I used Lovelock theorem 2. Okay, Lovelock, according to the Lovelock theorem, I get, also I discuss SH is equal to SM plus KSM. Okay, so now I used Lovelock theorem 2 and I get this value equals to 0, and now simple derivatives, and I proved Einstein-Field theorem. This is my Einstein-Field theorem. This is my EFE. Thanks for watching. I hope my video is very helpful for all people. Okay, this is my discussion is with matter field. When I used matter field, then I can say S is equal to SH plus KSM. Okay, in here SM is the matter field, action is matter field. So I use, and after that I use the variation with, we can write variation in action del S using field Lagrangian. Okay, I used field Lagrangian. This is my, I use field Lagrangian. Thanks for watching. I hope this proof is very interesting for every physics learner. So friends, this is